What do a cheap loudspeaker and a smartphone have in common? Simple. They both sound bad. Nowadays, people are so used to high audio quality that they hardly tolerate poor listening experiences. Anyways, on the one side, not everyone can afford always a hi-fi loudspeaker. And on the other hand, smartphones, which do mount small-sized loudspeakers, have physical limitations that challenge the design of efficient method for improving the audio quality. What if I tell you that it's possible to make a cheap loudspeaker sound as a high-fidelity loudspeaker? Or what if I tell you that it is even possible to induce the perception of low frequencies where they are not present? In other words, what if for having a good-sounding loudspeaker, you no longer need a lot of money and, for example, speaker characterized by super linear displacements, and that is even possible to cheat physics? We sound better. Our idea is that the basis for the development of digital signal processing algorithms for the loudspeaker linearization, compensation, and virtualization. The approach is based on the inversion of loudspeaker models that inevitably must take into account all the physical domains involved in the transduction process. In fact, the performance of an audio system strictly depends on the nonlinearities affected in those physical domains, and as well as on how those domains interact. We thus derive digital techniques to derive the digital implementation of the audio systems, like taking into account multiphysics LAMP models that are at the same time characterized by efficient and efficient and signal processing oriented. We do this we're using wave digital filters that allow us to implement the design of efficient and modular structures, and in this domain, we demonstrated that it's possible to easily invert and explicitly invert in loudspeaker models. In fact, for the task of loudspeaker linearization, we obtain a reduction of the total harmonic distortion by 20 dBs. And moreover, we developed algorithms that are able to increase the perception of bass frequencies, taking advantage of psychoacoustic effects. And in this task, we actually got an improvement on the 25% as far as bass enhancement is concerned with respect to state-of-the-art method. So our methods basically differ from like technological and closed-loop solutions. For example, as far as cost and portability are concerned, and we develop. With this algorithm. These algorithms are super easy and ready to use, and it means that basically we can potentially make whatever loudspeaker sound better. So let's take a look at the market, and the overall speaker market is worth 39.6 billions, where a huge share of the market is around the 60% is taken by small-sized loudspeakers, while just the 40% is taken by large and medium-sized speaker. If we take a look at an estimate for the compounded average growth rate for the years 2020 up to 2027, we see that the market is growing, but we have another very good news, that the share of the market that will grow the most is that related to small-sized loudspeaker, which is basically the target for our algorithms. In fact, there's a growing interest towards small-sized loudspeakers in different fields of the market. For example, for different applications, like ranging from biomedical devices to consumer electronics and automotive applications. So here I summarize the roadmap, and like merging both traction and future steps. And we acquired, in particular, some fundings and industrial partnering in 2018 and 2020, and we have filed 2 different international patents, one of which has been granted while the other is still pending. This is the team, and the team is composed of highly professional figures and that have like different expertise and skills that are somehow complementary. So I am Riccardo Giampiccolo, this is Wave Audio, and I thank you for your attention.